Hello, how are you? So this Tuesday, I have a doctor appointment at East Brunswick at 11 a.m. I'm not for sure that I can come back at the classroom at 2 o'clock. So it seems that uh, we use video lecture may be better. So today we just use video lecture. Okay, okay, thank you. Okay, okay. Ah, so today's topic is a continue of one-way table, two-way table, those things. Ah, so we know what is one-way table meanings, what the two-way table meanings. So those are typical example for one-way table, two-way table, right? So two-way table compare uh, many classes. A one-way table just we have only one class. Okay. So the typical question for two-way table, one-way table is just like that. Like changing this direction make a difference. Like here, changing this direction make a difference. Or these three classes, their grade distribution quite the same, or have a significant difference. So for one-way table, we can say that changing this direction make a difference. Okay, so we say for in this example, we say changing this direction make a difference. Such a problem not so interesting. So maybe the most interesting question for one-way table is like whether the data match the model or match our assumption. Okay, so we say changing this direction make a difference. We also can we assume that if no difference means the percentage the same, right? We also can say changing their percentage the same, but changing this direction make a difference. So sometimes we do have those questions. If those questions make sense, right? Okay, so we say so the idea is if the data match the model or match our assumption, then based on our assumption, the data should be looks like that. So those data, we call those data the expected value, right? Then we compare whether the true data or observed data and our expected data are close or not so close, right? Okay, so now let's consider the problem. Like, is there grade inflation in our class? Like maybe our department chair maybe blame me our class do have too many people got A, too many people got B, like that, right? So here, suppose I wanted to defend myself. I wanted to say no grade inflation, or have the grade inflation or no grade inflation. How can I prove this? So no grade inflation means our grades also match the padding or the model. So suppose the for other people or the model or padding, we can say there's a padding or model. Mm. So like for getting A, like 20% getting A, 30% got a B, or 40 usually like a 40 C, 10% D or F. Then we want to check whether those data match these percentages matches the model. Okay, so we find expected value. So if based on this model, based on those percentages, how many should get A, how many should get B in our class? So we say we can find the expected value, right? So those expected value just a percentage multiplied by total. Like here, how many can get A? So 20% get A. Then totally, how many students? So here we see in our class, so totally we have 30 students, right? So 20% of 30 is 6. So this is expected value. Saying this 9 is expected value for get B. So B is 30%. So 30% got B, 30% over 30 of 30. 30% of 30 is 9, right? So we can easily find those. If 40% of 30 is 12, 10% of 30 is 3. So then we just check source observed data and supposed data are close or not so close. So determine this, so we find chi-square value. So this chi-square value is this formula, right? Chi-square value is summation of observed value minus expected value square over expected value. Okay, so we just check out this cell 6 minus 6 square over 6, 12 minus 9 square over 9, 8 minus 12 square over 12, 4 minus 3 square over 3. So in this, usually we say chi-square value is calculation is tedious. But for this simple case, calculation is okay, right? So for this simple calculation, maybe I will ask you to do the calculation. I will ask you what is the chi-square value for this problem. Okay, so let's say for those simple calculation, you should be able to do those. I will check your understanding for the formula. Okay, so by a little bit calculation, we find that this value is 2.67. Then we need to determine this number is big number. Can we say this big? Or can we say this is small? So we need to determine the big number or small number. So determine big or small, we just check a chi-square table. So for chi-square table degree, so we need to know degree of freedom. So for two-way table degree of freedom, we use this formula r minus 1 times c minus 1, right? This is the formula for two-way table. So here R means number of rows, C means number of columns. So if we apply this formula to here, we say our R equal 1. So 1 minus 1 times C is 4. 4 minus 1. Oh, this is okay. So this equals 0. So this means this is not good. And so here for two-way, so we cannot use the formula from two-way table. So for one-way table, degree of freedom, we use this formula, C minus 1. Okay? So degree of freedom, so here C is 4, so C minus 1 is 3. So actually, this degree of freedom, why this degree of freedom is 3, this is easy to explain. Like we in our class, how many A, how many B, how many C, or D, or A, So those number can change. Like we don't know how many how many people get A. Could be 5, 6, 7. Right? Could be those numbers. So those number got A or got B, or those numbers we don't know. Or those number can change. But so total number 30 is fixed, cannot change, right? Yeah. So like in our class we have 30 students, so just give some people A, some people B, right? So we say like, okay, so we have those 4 numbers, but these 4 numbers have the relationship totally is 30. So if we know if we know how many A, how many B, how many C, then we can find how many D or F, right? Okay, so this means even though we have 4 numbers, but we have only 3 numbers can change freely, right? The last one is fixed. So this is the reason the degree of freedom is C minus 1, right? Okay, so if we know degree of freedom, then we can find the critical value, critical chi-square value or chi-square critical value. No, degree 3. Oh, I'm sorry. This I made a mistake. And so the critical value determine the degree of freedom and alpha, right? So we find the number is this 7.815. So judged by this, so we can say this number is small, 2.67, small number. So this small number means the data and the supposed data, or the data and this assumption or model match quite well. So I can say in our class, no great inflation, just the match this pattern or match this model, right? Okay. So here we say so this here calculate this number, test statistic is important, and find the critical value is also important. So I will check those questions, right? So how can we get this 7.815? So we say check a chi-square table, or maybe I'll put a chi-square table here. Yeah. So degree of freedom 3, then check this line, and so this is alpha, right? Yeah, 0.05, so we find this number. Okay. So we say for one-way table, we can regard a one-way table or two-way table. Those are categorical data, or we focus on percentage proportion. What is the percentage in this cell? What is the percentage here? What is the percentage here? So we just talking about percentages or proportions. So two-way table, one-way table, we can regard those compare many percentages. Okay. So now let's consider there's a problem. Is the landing machine really landing? So we discussed those problems before, right? We just compare two percentages, right? Okay. So and we also, let's say, to answer this question, we can regard this is we can regard this we can focus on one percentage, like let's say suppose like I just consider, if I just consider this the percentage for getting digit 4. So let's say percentage from the data, it seems get this digit 4 is 1050, right? And supposedly this percentage should it be 10, right? We have 10 digits. So if the landing machine delay landing, then each digit should have 10% chance to appear. Okay, so we can check. Sorry, we can check whether whether this p for equal this or not equal this. We can check this, right? P4 not equal this. So we can regard it as the one sample problem, right? So this is one sample problem. We just focus on this. We forget others. Okay, we just pick one. And we also can regard this two sample problem. We just pick we just pick like a digit 4, other one digit 8. So is these two are the same or have a difference? Like we say like here we want to check P4 percentage for getting 4 or percentage getting 8 equal not equal. We can check this, right? So this become a two sample problem, right? And also we can check this, or let's say we can check whether all are equal. Percentage for 0 and P1 equal P9. We can check all those percentages. So this is just like a many sample problem. Like we compare many percentages. So for this one we use one-way table. So we just check like in this direction make a difference or no difference. So this is HO is just no difference. Okay. So if there no difference, then each one should be 1000. So its expected value should be 1000, 1000, 1000, right? 1000, 1000 for each digit. Oh, sorry, 1000. Okay, like that, right? Okay, so we can find the chi-square value. So the chi-square value is this, right? Chi-square value equal formula summation of the observed value minus expected value square over expected value. So for first cell, so this is 935 minus 1000 square over 1000. Then second cell, this minus 1000 square over 1000, like that, right? So this calculation, if we use calculator tedious, so we need some tools for calculation. So for those calculations, Excel is okay. So in Excel, those calculations is okay because in Excel we can type the formulas. Okay. So for complicated calculation, we need computer programming, right? So for stats application applied stats 2, we use computer software. Okay, but anyway, like we say, we find the chi-square value is 35.8. So again, then we want to determine this big number or small number. Okay, so we need to find critical value. So for critical value, we need to find the degree of freedom. So df degree of freedom is c minus 1. So c equal 10, right? Yeah, so 10 minus 1, 9. So we check this critical value, make one decision. So let's see. Do I have the no? Oh, so I need to check chi-square table. Yeah, I need to open another table. But anyway, like I assume you can check the critical value. So I just leave this for you. Find the critical value, and the critical value is the degree of freedom, and also based on alpha, right? So suppose alpha is 0.005. So with the degree of freedom and alpha, we can determine those critical value. Then we can judge this is big number, this test statistic is big or small. So our conclusion, say we find this number is, we judge it, we say this number is a big number. Okay, so big number, then our decision or our conclusion is this landing machine is not so landing, because like let's say typically, digit 1 appear too many times, digit 0 appear 10, 90 is too high, 930 is too low, right? Okay, so those are 2 examples for one-way table. Okay, so we say one-way table, two-way table, those are a generalization for compare many proportions. So we already have those discussed those questions, compare 2 proportions. So by now we can compare many proportions. So those we can regard like compare 2 proportions or 2 sample problem or many sample problem, many proportion or 2 proportion. So for 2 proportion, just like ANOVA, we say sometimes ANOVA is compare many, and but for 2 we usually use T, right? T-test for 2 sample problem, or ANOVA for many sample problem. But we also can apply ANOVA to 2 sample problem, right? So here the same story. We also can apply 2-way table, 1-way table for compare 2 percentages. Okay, so now let's consider this problem. Okay, we discussed this problem before, right? We have 2 candidates. We wanted to predict who will win, right? Who will win the election. So we just usually do a survey, right? Do some poll. Some agency just did that. So okay, so we have this result. We say for candidate A, we have checked 1,000 people and find 220 will vote for him. Okay, so we get from data from our survey, we find percentage for candidate A or P1. We say this equal 42, right? So we can say from our survey, it seems 42% people will vote for him. And the same for B, we checked 2,000 people and found 900 will vote for him. So percentage for B, candidate B, is 45%. So from what survey we found 45% people will vote for him. So from our survey, from the data, we find they have some difference, so 3% difference. So the question is 3% difference is significant, big enough? Okay, we say like B will win the election. So for such a problem, so we can regard this as compare two proportions, right? So we can use two proportion compare two proportion. We can use two sample z-test. So z means proportion. We can say two sample usually t-test, but the sample size is quite big. The z is usually become t becomes z. So we can use this formula. Test the statistic thus: z value equals thus. So we put here the calculation x bar, so we can regard this is x bar is 42, right? And the data is just 10 data, right? So 42, 45, and so S1, so for 10 data is PQ, right? It's 1 square just P hat, Q hat, okay, PQ. So this equal 42 times 58 over 1,000. I'm sorry. So plus, so here is 45 multiply 55 over 2,000. Okay, then after a little bit calculation, we can find this number, then determine this number big number or small number, right? This number so or close to 0 or not so close to 0. So we need to determine this. So determine this, we can use p-value, or we can use p-value, and we also can use the critical value. Okay. So here for critical value, so we say for the critical value, we also have like one tail. We need to check one side or two sides, one tail or two tail. So here one tail, two tail is up to us. So how can we determine one tail, two tail? This depend. So whether we wanted to. If we wanted to say thus PA less than PB, then one tail. If we say PA not equal, just simply we check they are quite the same or have a difference, then this is two tail, right? So in here maybe we just check one tail, because we will check this whether this guy will win the election, right? The PB is larger than PA. Okay, so we say for such a problem, we also can convert two-way table problem. So we just check it out. We can change this as a two-way table. So for candidate A, so we just split people by two categories. People will vote for him. People will not vote for him, right? So vote for him, so totally 1,000. So vote for him is 420. Not vote for him, 580, right? So for B, vote for him 900. not word for him is 100, right? So we just check this way, no difference. So we can put it together. So we say we here word, so put it together. So this is category 130, and here here is let's say one. I made a mistake. Okay, 20. 1680, right? And totally 3000. Okay, so we can find what is the percentage uh, for what for what. This percentage is like this: 1320 over 3000. Okay, then we can find is 1 So is 1 here, meaning it's like how many supposedly to vote for him. So E1 equal this percentage for what for this this category. No, I'm sorry. Okay. Then multiply totally 1000 people, right? So we can find those expected value. Then we can use two-way table, find chi-square value, then determine this. Okay, so just let's say, just like we apply ANOVA to ANOVA to two sample problem, and here apply two-way table to two proportion problem. So we can use this ANOVA or two-way table, but the difference is HA. For two-way table, we can say if we compare two-way table, HA could be not equal, right? P1 not equal P2, or could be larger than, or could be less than. Okay, but for two-way table or ANOVA, we only can check this, right? Equal or not equal. Okay. Okay. So let's say, so if we can use two-way, if we can use two sample problem, we just prefer two sample problem. We can, so for this problem, maybe we prefer we use compare two proportions, not two-way table. Even though two-way table works, but the two-way table only check the distribution for what for him or will not what for him, the same or not the same. Okay. Okay, so we can say like so we do have many examples for two-way table. Like here, if we split people by two categories. So more generally, we can split people by many categories, right? So then we have many proportions of two-way table or one-way table. Okay, so for example, like a student evaluation. So by the way, at the end of the semester, you are supposed to give a faculty member of your teacher a teaching evaluation, right? And and also you should give me your evaluation, right? So I hope you can take some time to do a survey and finish the course evaluation. Yeah, and so I hope you again like I hope you can be nice. Okay, but anyway, suppose like okay, so so course teaching evaluation usually not good or bad. We split like a 5 category. So we use those numbers like points. So 5 means very good, very good. So 1 not good, right? So 3 is between. Like 4 is quite good. So like 5 is really good. 4 is good. Like 3 is average. Just like that, right? So suppose like here I got the result of like so many, say like 20 give me 5 points, 18 give me 4 points, like that. And the other one is just like that, or only 15 give the other professor 5, and 24 give him 4. Okay, so then like suppose I want to prove my teaching evaluation is better than others, better than other professor. So this problem could be like two-way table problem, right? If we two-way table problem, if we check all category. So if I just focus on this category, so this become 2 proportions, right? We just check this. Okay. Okay. So we just check it. Only check this. Oh, check all. Then check all the two-way table. Okay. Okay. So let's say as in our report, usually like we'll give the average. Let's say like okay, so we can find so for my, let's say, how can I find average total points? Let's say like so just let's say 20 give me 5, 18 give me 4, like 12 give me 3 plus. Then divided by totally how many students? 20 plus 18 plus 12, like that, right? So use this. Suppose my point is let's say, let me say, like 4.31. Suppose other one is 4.02. Okay. So we also can change those as numerical data. Like we have like a 5, we have 20 data like that. Data 5, thing 4. Data like that, right? So we can, and other one is they just we have those data 5, only 15 5, but 5 thing 4. So we just have those data. So we can regard those just numerical data, and we want to compare the mean. Okay, so this mean actually just like we say weighted mean, or this mean just like over like calculate over GPA, right? If you graded A, it give you 4 points. Changing this, just changing the grade, changing the category to numbers. Okay, like you grade is A, changing to 4. Grade B, changing to 3, right? Okay, so just changing category to numerical. Okay. Okay. So so those the today's topic. So we can say we covered the typical some typical problems in stats. So we can say in stats just have one sample problem, two sample problem, many sample problem, right? We have those like one sample or two sample, many sample problem. Okay, and for each one we can split as two. Like if data for data is numerical data, or categorical data. Okay, like so we have one sample numerical data, one sample, just those one sample problem. If one sample categorical data, just this one sample, just the one-way table, right? So two or many categorical, this is just the two-way table. Okay, and also so categorical data can be changed into numerical data, and numerical data sometimes also can change to categorical data, right? So for example, like we wanted to, let's suppose we have the data. So we want to check this question like is data from normal. So data from a normal distribution. Okay, so how can we check those? So we just put those numerical data into categorical data. So idea is, let's say, idea is for let's say for normal distribution, we have thus, like we have 68, from here 68, we have thus 68, the 95, 99.7 law. So this means from this is kind of 68% people, 68, and here 95, and then from here to here 99.7. So now suppose we have 100 numbers. 100 numbers. Then we can split it into some categories. So in here should be half of 68. Should be 34 numbers in here, 34 numbers here, right? And so from here to here, let's say 95 minus 68 equal, we should have 27. So 27, this half should be like 27 over 2 should be 13 or 14 here, 13.5 number here, 13.5 number here. And then outside here only 2.5 numbers, right? Maybe like 2.5, yeah, 95, 2.5 numbers here, 2.5 number here. So we just check like your data based on this your data, like suppose like in your data in here only 20 here or 40 here, 40 in this category, in this interval, then 10 here, 5 here. Okay, so then we just check whether your data and supposed number, supposed number is like 13.5 numbers here, but your data 10 number here. So we just check whether they are close or not so close, right? So this is just we change this to one-way table. And This test, by the way, is important in stats. We call this as a goodness of fit test. Goodness of fit test. We just test whether the data fit our model, fit our assumption. Okay. Okay. So we say in a short, those are all most the stats. So the typical stats question. One way, one sample problem, two sample problem, many sample problem, and also depends on data numerical or categorical. And also we can change categorical data to numerical data, or numerical data to categorical data, right? Okay, so we have one more just a question left. Okay, so but anyway, like we can stop today's class. Thank you.